Hello, my name is Ashley Gibbon. I'm the development manager, and this training is about the principles of assay linearity. So this is the first of several trainings on the various parts of a validation. So it's geared towards the development techs. I want to make sure that we're all on the same page about what's involved in a validation, what do the regulations state, how do we set up our experiments, how do we look at the data, how do we write it up, and then once we launch an assay into operations, how do we maintain it? So if you've got any other ideas on trainings you'd like to hear about, let me know. The first 5 we're going to do is linearity sensitivity, which is this one. We're going to do one on precision, one on accuracy, one on sample stability, and one on reference range. So what are we going to talk about today? Here's our topics. What is calibration and why do we do it? We're going to cover some common terminology around the topics of linearity and calibrations. The bulk of the talk is going to be on how do we determine the linear range during validation. And then once we launch that assay into operations, how do we confirm that linearity? So everything that I'm going to talk about today comes from the Clinical Laboratory Standards Institute. This is an internationally known organization that has hundreds of different documents on how to do everything in the lab. And basically, if you're following the CLSI guidelines, then most regulatory bodies are fine with you. So CMS is fine, New York is fine, as long as we're following the CLSI guidelines. So this particular one is the evaluation of the linearity of quantitative measurement practices, a statistical approach. So what do they have to say about calibration? A quantitative analytical method is linear when there exists a mathematically verified straight line relationship between the observed values and the true concentrations of the analyte. Now this is kind of heavy, and those documents are all pretty heavy, so we're going to break it down into plain English. Think of your calibration like a measuring stick. So we've all used the ruler before. You have the demarcations, 1 inch, 2 inch, 3 inch, 4 inch, right? And these are internationally recognized units of measurement. So this means that you can go anywhere in the world. You can go to Wichita, Kansas. You can go to St. Petersburg, Russia. You can go anywhere and buy a ruler, and 1 inch is 1 inch, 1 inch. So really what it enables us to do is communicate with our clients what their patient results are. So a calibration curve, instead of being 1 inch, 2 inch, 3 inches, might be 10 milligrams, 20 milligrams, 30 milligrams. And so by measuring on our calibration stick like this, it enables us to talk to the clients and say, your patient has, for example, 20 milligrams per milliliter of lactic acid in their urine, and they will know what that means. So how do we create our calibration? Well, we're going to purchase or create solutions of a known concentration. So what does that mean? If we're validating a commercially available kit, say maybe an EIA, where you're just opening the box and reading the instructions, oftentimes they will include an entire calibration set for you, and that's absolutely the easiest way. So if we can do that, let's do that. But oftentimes we are creating an assay new, or we're having to create our own calibrators. So we need to purchase a known solution of our analyte. So there are certified reference materials, and these are sort of the gold standard. If you can get those, that's great. There are commercially available calibration sets where you can purchase from a second manufacturer. Those are always nice because you've got a second set of eyes basically verifying the values for you. But in a lot of cases, those sorts of things don't exist. So in those cases, we're going to purchase stock powders or solutions of our analyte of interest. So we're going to go to Sigma or Fluka or something like that, and we're going to purchase powders of, say, lactic acid. Let's stick with that example. So we're going to purchase a powder of lactic acid, and we're going to very carefully weigh out exactly what we want. So say exactly 100 milligrams of this powder, and we're going to dilute it into, say, 100 milliliters of water. Obviously, this is going to be assay specific, but stick with me for illustration purposes. So once we've created or purchased our stock solution, we're then going to make multiple dilutions of that stock. So let's stick with my example of 100 milligrams per milliliter solution that you just weighed out. Then say we're going to do a 1-to-1 dilution 4 times. So we're going to end up with 5 tubes, one with 100 milligrams per milliliter, one with 50, one with 25, one with 12.5, and one with 6.25. Okay, so that we now have 5 solutions of that analyte at varying concentrations. We typically target about 5 to 7 points, but that's going to depend on the assay. We're going to run these solutions as unknowns on our assay and then see what comes out the other side. So whatever sort of results that your instrument or your plate reader or whatever is going to give you. So this might be responses, optical densities, counts, whatever. And we're going to graph those. As you can see here, so the y-axis is our target concentration, and then the y-axis is going to be the observed response. And there are lots of variations on this, but typically concentration on the x, observed on the y. We're going to draw a best fit line through this to create the calibration curve. And so these points become anchors, allowing us to interpolate the concentrations of samples along this calibration curve. So really what this does, it means that we can give clients their patient results all along this line without having to run a calibration point at every single part of the curve. So how do we do that? We use the equation of the line. This is a really simple one, y equals 100x. And we're going to read our patient responses off. So for example, we have a patient with a response of 723.54. We plug that into the y, solve for x, and we get a patient concentration of 7.2354. So this is just an example, but you can see how we didn't have to run a calibrator at 7.2354 because we created our calibration curve and we confirmed it during validation, which is what we're about to cover. But I wanted us to make sure we understood what a calibration curve is up front before we get any further. So we create this curve during validation, and then we confirm it during validation. And then once we've launched it, it's confirmed every 6 months by performing a linearity or a calibration verification. Those are the same things, they're just we use different terminologies in different places. And again, by confirming the calibration every 6 months, we can then give accurate patient results all along that calibration line without having to run multiple calibration points. So whenever possible, we'd like to matrix match our calibrator. So what does that mean? You remember when I mentioned that we're going to weigh out 100 milligrams of that powder and dissolve it into a solution. Well, maybe instead of dissolving it in water, we dissolve it in urine or in blood or whatever our particular sample matrix is. This does a couple of things for us. For starters, it gets our calibrators as similar as possible to our patients. So if there's any sort of matrix effects or matrix interference present in our samples, we're matching our calibrators to that same effect. So for example, let's say that there's something about urine that masks 2% of our analyte of interest. If we have a calibrator in an aqueous solution with no masking, and then we try to run patient samples against that curve, we're not going to account for that interference and that masking. Obviously, this can cause problems. Because of interferences, sometimes that doesn't work. Sometimes if you're going to make multiple dilutions of the calibrator, we get to a point where if you make 5 or 6 or 7 dilutions, by the time you get to those lower calibrators, you've diluted out any matrix effects. So there's a lot to consider here. It's sort of a good practice. And if we're getting into an assay that we're developing and we're unsure, let's have this conversation. Let's talk about when does it make sense to do matrix calibrators versus aqueous calibrators. A couple more things to pay attention to when you're creating a calibration curve. You really need to pay attention to the certificate of analysis and then adjust your calculations for purity. So this can take 2 forms. The most common one is something like this. You got your certificate analysis for beta-hydroxy isovaleric. And in this particular lot, if you look down here at the bottom, you can see this is only 97.4% pure. So this means if we weigh out 100 milligrams of this powder, only 97.4 milligrams of that is actually beta-hydroxy isovaleric. So moving forward, you either weigh out 100 milligrams and then call it 97.4, or you weigh out whatever the math is, 102.6 milligrams and call it 100. It's just important that we're documenting what we're doing and calling it the correct thing. Secondly, sometimes we can't find the pure forms of the analyte of interest. So this is an example of sodium D-lactate. This is a product that we use as a second source for lactic acid. So what does this look like? This is the chemical structure. It's the lactic acid with the sodium addition there on the right. And this is what pure lactic acid looks like. So you can see where there's that sodium ion that's replaced the hydrogen. So what does this mean as far as your calibration? So lactic acid formula weight is 90.08, and sodium lactate formula weight, the sodium version of lactic acid, is 112.06, which makes sense. The math works. The molecular weight of sodium is just under 23, and the molecular weight of hydrogen is 1. But what does this mean if we're actually weighing out powders to make a calibration solution? It means if we weigh out 100 milligrams of this particular stock, only 80.39 milligrams is actually lactic acid. The rest of it is the salt. That's how we found that math there. So you just need to pay attention to this and make sure that you're accounting for these sorts of things. We try not to use salt forms if possible, just because it can have other impacts that you may not be thinking of. I mean, in this particular case, it's sodium, so this could have effects on the buffering capacity of your solutions, of your calibrators. There could be other issues down the road. It may not make a difference. So it's really just about making sure that we're documenting what we're doing, we're adjusting for any sort of impurities like this, and being aware of the potential ramifications. So let's talk some about the common terminology around linearity and calibration. In the lab here at Genova, we talk a lot about calibrators and standards, and for the purposes that we use them for, they are the same thing. And I hear people using them interchangeably, and that's fine. You can use either one, and I will know what you're talking about. But these are two, reportable range and reference range, are two terms that I hear mixed up pretty commonly. So I just want us to take a few moments to talk about the differences between these two. The reportable range, the CAP, which is the College of American Pathologists, defines as the lowest and highest numeric results that can be reported after accounting for dilutions and that sort of thing. So this is our measuring stick again. So the reportable range of our ruler is 0 to 12. Our assay can measure 0 to 12. 13 is off of our stick. 13 is outside of our reportable range. That makes sense? It's pretty straightforward. This is something we're commonly thinking about in the lab. The reference range, however, refers to the clinical interpretation of the final results. It's the normal range for our analyte of interest. So this is a term that's more commonly used by our colleagues in medical affairs and client services when they're speaking to the clinicians, to the clients about their particular patient results. They're going to refer more commonly to the reference range. So here's the way I think of it. So let's say we're using our stick to measure a widget. We have this widget assay, right? And this particular widget measures 1.2 inches, right? That's totally within our reportable range, no big deal. So during validation and development, if we don't have a reference range provided by a manufacturer or by the literature, we're going to have to create our own. So what we might do in our widget assay here is we're going to measure 100 widgets. And let's say that we find that out of the 100 widgets that we measure, 98% of them fall between 0.8 and 1.4 inches. So now we can say that we expect that most widgets that come in the door are going to fall between 0.8 and 1.4 inches. This is your reference range, okay? So in this illustration, 0 to 12 is our reportable range. That's what we can measure. And 0.8 to 1.4 is our reference range. You see the difference? So one's about what we can measure and one's about what we expect. So in the lab, typically we're just talking about reportable range. You're running your assay and you want to know what's the range at which I can release patient results. The reason that reference range might affect you is that let's say our widget assay here that we're expecting them to fall between 0.8 and 1.4, and you're running your widget assay and it's coming out the same every day, and then one day you get a widget that's 6 inches long. Is that a problem? No, not for you. Your reportable range, 0 to 12, 6 is right smack dab in the middle. You can see 6 inches, no problem, right? But that's really far outside the reference range. So that might be a clinically important point of the assay. So if we released a patient result at 6-inch widget, that might be the point at which a doctor says, you know what, this is a marker of, I don't know, cardiac disease, and we need to treat this patient based on this result. So there are times when if we get a result that's, even though it's within our reportable range, it's far outside of our reference range, we might ask you to repeat it. So a lot of our SOPs have this written in where it might say our widget assay can report from 0 to 12 inches, but any result over 2.5 inches, we're going to repeat for confirmation. So if you've ever wondered why you're repeating things that are well within your reportable range, that's why. It's because our clients might be making medically important decisions based on those kinds of results. So let's talk about sensitivity. This is something that confused me a lot when I first started in development, because we have these 4 terms: functional sensitivity, detection limit, limit of quantitation, and limit of detection. And I would get them confused all the time. I spent a lot of time saying, wait, what are we talking about? And it turned out that I was getting confused because for what we're doing, and these 3 basically refer to the same thing. And limit of detection is something different. And so you can see why that's confusing, because detection limit and limit of detection, they sound like they should be the same thing. But for our purposes, the functional sensitivity, detection limit, and limit of quantitation are the same thing. I want to take a caveat here if there's anybody from medical affairs or client services listening. There's a different definition for detection limit often when we're talking about clinical utility and that sort of thing. Detection limit that I'm speaking about is specific to the technical part of the assay. So what are the differences? Limit of detection is how low can we measure before that signal just becomes noise or background. And these 3 are how low can we measure and still get acceptable precision and accuracy. So for those of us in the lab, I think of this like the limit of quantitation, the LOQ, is how low can I go and I'm still getting acceptable CVs, I'm still getting acceptable precision. Basically, how low can I go, and if I get a proficiency test sent through, I still feel confident in those results. I still know that I'm going to get the right answer. Limit of detection is really at what point can I not differentiate my result from noise. And I'll show you some more on that in a minute. So how do we determine these various cut points during validation? We have 4 experiments that we run. We run an aqueous linearity, a matrix linearity, a functional sensitivity, that's our limit of quantitation, and a limit of detection. For all experiments, you want to use a second source material. You cannot use your calibrator material to confirm your calibrator material. I cannot stress this enough. And this is something that we don't always think about, but it's vitally important, because if there is a flaw or an error in your calibration material and you use it to check itself, you're not going to be able to catch the error. So say this is our calibrator. So there's something kind of funny about that, but if you're using a calibrator to check your calibrator, you're not going to catch that error. But there's an error there. You see how we need to do a second source material as that last ruler to prove that there's something going on. So ideally, you're hoping that your second source material absolutely confirms your linearity. That's the best case scenario, but they have to be 2 different sources. Ideally, the second source is from a whole different manufacturer, a whole different company. There are some situations where there is only one global supplier of a certain product. In those cases, we want to, at the very minimum, go for a second lot number. And there are a few rare cases where we have to get there are no suppliers of those analytes and we have to have a custom synthesis. And these are okay. They're not ideal, but they're okay. We just need to manage them very, very carefully. So if you're in an assay and you can't find second source material, make sure you're telling me, make sure that you're raising it to the lab directors just so that we're aware and we can figure out how to manage that and make sure that we're getting the highest quality validation. And again, we need to make sure that we have a certificate of analysis for all of these materials so that we can make sure we're checking for purity, for documentation, that sort of thing. So how do we run our aqueous linearity? It's a lot like our calibrator. We have a stock solution, that's that 100% A, and then we dilute it out at multiple levels and run them as unknowns. There's a lot happening in this slide. The levels don't need to be equally spaced. Basically, it says just be careful when you're pipetting small amounts. Watch out that you're considering solubility. Sometimes things don't stay in solution. Sometimes you have a really sticky, oily substance, and those can be hard to pipette. If you're working on any assays that have enzyme sources, you need to make sure that you're choosing enzyme activity that's equivalent to human source materials. We don't have a whole lot of these in the house, and they're not actually that tricky. You just have to pay attention to them. So if you get into an assay where this is the case, let's talk about it. So the goal of aqueous linearity is to confirm those calibrators. So you created your measuring stick, and now you're using a separate measuring stick just to make sure you're getting the same answer, right? If you're validating one of these commercially available kits, this is pretty darn easy because the manufacturer is going to tell you what your reportable range is, and you just measure that. In cases where we're creating our own reportable ranges, we may not know what our reportable range is going to be. So in those cases, it's a good idea to go 20 or 30% wider than your anticipated measuring range. And that way you can see not only where does the reportable range work, but where does it stop working. This could be anywhere from 7 or more concentrations. You run across the anticipated measuring range, and you do 2 to 4 replicates at each level. I like to do at least 3. So let me show you what that looks like. Here's a validation we did where we didn't have any idea what the reportable range was going to be. So we ran 14 levels. It's 4 orders of magnitude from 1,000 to 0.12 micrograms per milliliter. And we made up all 14 of these solutions by serially diluting, and we ran them in triplicate. Here's the 3 replicates. And then we found the average observed value, and then we had 3 ways that we assess the data. So first we look at CVs. So CVs is your standard deviation divided by your average and then put into percentage form. And the CVs tell you how reproducible your replicates are. So it's not taking into account what your expected values were. It's just looking at, okay, for level 5, for example, I got a 1.84, a 1.62, and a 1.85. How similar are those results? How tight, how reproducible are my replicates if I'm shooting just the same thing over and over again? The acceptable CV is going to be assay specific, and when you start into a validation, we'll have some general guidelines to tell you, like for this assay, let's start at 10% or 20%. But it might be the sort of thing that as you get further into validation, you might come back to this linearity and tighten or widen your CVs depending on what you learn later on in the validation. In this particular example, we set the CV at 20%. So you can see that between level 3 and level 4 is where we start to lose our reproducibility. We also look at percent error. So error is the difference between your observed and expected divided by your expected, and then to a percentage. So this is a measure of accuracy. So what this is comparing is how does my average observed compare to what I expected to get? And so again, this is going to be assay specific. You may revisit it. In this example, again, we set error at 20%. So we use these things sort of in tandem. The CV tells us how reproducible we are. The error tells me how accurate I am. So how can I get the same thing every single time, and can I get what I expect to get? And so you can see in this example, what I'm looking for when I'm setting a reportable range is where is the area of this experiment where I'm getting acceptable CVs and acceptable errors. So it looks like the bottom end, about 1.95 up to 500. So there's one more piece of information we need before we set the reportable range. So we plot the expected concentration on the x-axis and the average observed value on the y-axis. And again, we draw a best fit line. And we're looking at slope. Closer the slope is to 1, the better the correlation. So that's telling me how close were my average observed to my expected concentration. We also will often look at the y-intercept, as close to 0 as possible, and then the r-squared. R-squared, you want to get as close to 1.0 as possible, and the r-squared is basically telling you how close are my points to that line, how tight of a fit is it. So you see how our points are pretty clustered around that line. If we had more of a spread, that r-squared would be a lot worse. So typically with r-squared, 0.99 is pretty darn good. But you can see in this example, this slope is not very good. It's 1.29. But it's because that top point is pulling it. So this, what I graphed here, was all of those points. And if you remember from a few slides ago, the error fell apart at the top level, that 1,000 level. So if we drop out the points that had unacceptable CVs and errors, like that, we get a much better linearity. So now we have a slope of 1.078, which is within 10%. So that's pretty darn good. R-squared got even better. So when you're going to write up your validation summary and you're talking about your aqueous linearity, this is the data we're using to set our linear range from arginine from 1.0 0.95 to 500 micrograms per milliliter. So this is showing, this is the data that we want to see in the validation summary. We want to see the replicates, the CVs, the error, and the linearities. When you're looking at your data, you want to look for obvious outliers, any sort of misplaced points, anything where something got typed in wrong. Look for drifts, look for trends. You can remove outliers. 1 or 2 outliers is okay. Any more than that, we need to start suspecting that there's something else going on. So let me show you some examples of when things did not look great. All right, can you guys see the error here? I mean, clearly it's something at level 4 because we see the CV and the error are not acceptable. And if you look, we expected 0.98, and what we observed was 0.93, 9.44, and 0.89. So clearly that 9.44 was some sort of problem. So most likely we just typed it in incorrectly. It was probably supposed to be 0.94, and we just put the decimal in the wrong place. So in this situation, go back to your run packet, make sure it was actually supposed to be 0.94 and correct the point. If it actually does say 9.44 in your run packet, then that's a clear, obvious outlier, and you can drop that out of analysis. How about this one? Can you see the problem here? So level 8, right, has an unacceptable error, but the CV is pretty good, right? So whatever it was, we were reproducible. We got a 43, a 38, a 38. So we're reproducible, but we're really far off as far as the accuracy. So if you look at this line, it was actually, the line 8 is higher than the line 9. So in this instance, I would suspect that something happened with that tube. You know, we made 14 dilutions. That particular tube, maybe we accidentally double shot it. I mean, it got contaminated. I'm not quite sure, but it's reproducible. So in this case, I would drop out level 8, repeat just that line, and see if that improves your error. How about this one? So this one is pretty ugly. You can see we got good error, percent error, right? We got what we expected to get, but the CVs are pretty bad. You're getting pretty bad reproducibility here. This is kind of a mess. If you get something like this, it's best just to repeat that because this is telling you that your assay is all over the board. If this repeats with a similar problem with the CV, then we need to look at your methodology because there's something going on with this assay. And how about this? This is sort of the opposite, right? So you've got really good CVs, but your error is off. So the really good CVs tells us that we got the same thing when we ran it 3 times, but we didn't get what we expected to get. So one thing you might notice here is if you look at your error, it's pretty consistently 22, 23% off. So we've got a consistent bias in our error. So in this case, I'd probably take a look. I'd probably question my second source material. So you look at level 14, we expected to get 1,000. So maybe I was trying to weigh out 1,000, but I actually only got 785 in the tube. So this happens sometimes. So in this sort of situation, I wouldn't get too concerned. I would remake my second source material, repeat the experiment. If it comes back the same, then maybe we should question the calibration material. I'd remake the calibration material, try it one more time. If that doesn't work, then we need to pause and figure out what else is going on. And this is an example of something we don't see, that we actually do see sometimes. There is one error here, but it's kind of hard to see in the data. So I'm going to give you a moment to see if you can figure out where the problem is. So what you'll notice is that the CVs are all over the place and the error are all over the place, but they're not consistent, right? So in this case, the third replicate is about 60% higher than the other 2 replicates. And if you drop that out of analysis, you get much better CVs and percent error. So in this case, we ran this set of 14 3 times, and something just happened with that third replicate. So what I would do is I'd repeat it one more time and see how your repeat looks. If your repeat looks like the first 2 replicates, then you've completed your linearity. But don't stop there. That's telling us something. If your repeat comes back like rep 1 and rep 2, what I would do is go back to that high run and take a look. Was there anything different about that run? Were the buffers different lot you have an expired reagent. Take a look at your controls. Maybe the controls for rep 3 were within range, but they were right up at the top of the range, in which case maybe we need to consider tightening the control ranges so that we don't get something like that in operations. So all kinds of things can cause problems with the data. Here's a list of some of the things: procedure instruments. Sometimes it gets too hot in the lab and that can cause problems. Interferences, bias, any of these can cause problems and bias. And we'll do a whole different training on looking at error and how to assess error. But if you're not sure when you're running your linearity where the problem's coming from, the best thing to do is just repeat it. And if it repeats the same way, then let's regroup and let's talk with the lab directors about what the next step is. Outliers are single results that can be visually different from all the other results, and you can remove one or two outliers. They are not multiple replicates at the same level. They're not one average level. That's a problem with your assay. So this is not an outlier. Remember we saw this when all of level 8 was off? This is not an outlier because it's reproducible. It happened 3 times. So this is something going on with your assay. There are a lot of statistical tests to figure out outliers, and again, we will talk about that during the error training, but the most sensitive test for outliers is a visual examination of the points. This came right out of that CLSI document. They said the best way to find outliers is just the things that pop out as just not right. You remember this one? So the 9.44, there's just clearly, that's just something different. So if that wasn't that we mistyped it, that is a clear, obvious outlier. And those can be removed without needing to be replaced. So let's talk about matrix linearity. Matrix linearity, we're going to run an awful lot like the aqueous linearity. The difference is just that instead of dissolving our compound in a buffer or water, we're going to dissolve our compound into a matrix. So we can run this like the aqueous linearity, where we take a sample, say a urine sample, with a high level of the analyte of interest, or we spike in the analyte of interest, that's this 100% A, and then we're going to dilute it down. The problem with that is that you can see as we get further down the dilutions, the 40%, the 20%, at that point you've lost an awful lot of your matrix effect. At this point it's mostly buffer or water. So another strategy is to take two matrix samples. So here I've got a 100% A in red on the left and a 100% B in blue on the right. These are two different samples. Let's say that A has a high level of our analyte of interest and B has a low level of our analyte of interest. And then we're going to mix them at various concentrations to get sort of a span of ranges. So what this does is it maintains that level of matrix across all of our linearity samples. So if there's any sort of masking or interference or anything like that, it's going to be consistent across the entire level. So, like I said when we were talking about matrix calibrators, there are pros and cons to being able to do this. I really like being able to mix the two patients together just so that I'm maintaining that same level of matrix. But that it makes some assumptions. It assumes that you've got two homogeneous samples that you can easily homogenize. So this works really well with urines, with a lot of blood samples. This does not work well with stool or with saliva, because as you can imagine, it's really hard to mix stool in the first place. So being able to mix two stools and then mix them at varying proportions, it's going to be really difficult to do. So you sort of have to consider your matrix and consider the best way to handle this. So why do we run matrix linearity? It's very helpful to run both an aqueous linearity and a matrix linearity. Aqueous linearity is best case scenario. It's never going to look that good again, right? That is perfect case. So then if you do the exact same thing in a matrix sample, then that's going to show you pretty clearly if they match, you are good to go. If you see any differences between those two as far as the linearities, the CVs, the errors, then that's going to give you some clues about whether you're going to have any matrix effects or interferences, or if there's anything about your sample that's going to change the values of your analyte of interest. And at this point, it's helpful to know, and it's helpful to compare, and helpful to talk about, but it's going to be very informative as we get into more precision and accuracy experiments. So let's talk about the bottom end, right? So in some assays, the low end is clinically relevant. So we might want to do studies to determine that low end. So remember when we were talking about the reportable range and we said, okay, we can go from 1.95 to 500. Oftentimes that's just fine, and we'll just set the low end at 1.95 out of our linearity. But sometimes it makes a difference in that particular analyte if whether things are very low or not. And so in that case, we're going to run some additional studies to look at the functional sensitivity, remember the limit of quantitation piece, um, to help us justify lowering that bottom end. So there's a couple ways we do that. If we know the expected functional sensitivity, like again, like an EIA or an RA or something where the manufacturer is telling us what the bottom end is going to be, then we find a second source material that's real close to that functional sensitivity, and then we run it as unknowns anywhere from 10 to 20 times just to confirm. So here's an experiment we did on homocysteine on the Architect. The manufacturer told us that the bottom end was 0.500. So we made a solution at 0.500. We ran it 15 times over 5 different runs. And you can see, again, we're looking at it the same way that we look at linearities. We're looking at CVs, this was 8.7%, and error, which was 5.3%. So this was, in this particular assay, we had a 10% limit. So this was good to go. We've confirmed the manufacturer's sensitivity. However, sometimes we don't know what the expected functional sensitivity. So, like one of those assays where we're creating our own reportable range. So let's say we want to dial in a little bit more into the bottom end. For example, if you look at this is one of those linearities like before, you can see there's a big difference in the percent error at level 2 and level 3. So at level 3, at an expected concentration of 0.49, we have an error of 8%. But at the next level down, at 0.24, we have an error of 42%. There's a pretty big difference. So the true bottom end of this assay is somewhere between 0.24 and 0.49. And in this point, it really does depend on whether this particular analyte, phosphoethanolamine, is clinically relevant at the bottom end or not. And that's something that we'll work with the lab directors to discuss. So it could be that they're fine with this and we just set it at 0.49 and we move on with life. It may say that they said, let's dial it in a little bit more. So how do we do that? Easiest way is just to add some more levels. So you can see we have the 0.24, 0.49. We added some levels in between. We're going to run them the same way. And now we can see that the error percentage goes from 17% at 0.39 to 21% at 0.34. So our true error is somewhere in between there. It may be that we want to dial it in a little further so we can run more levels. The other thing we can do if we have this kind of data is do a mathematical calculation. So we're going to take the target concentration and we're going to plot it against the percentage error that we're observing, like this. And then we're going to say, all right, we want to make the cut at a 20% error. So where on this line would a 20% error fall? What concentration? So a lot of math happens. We're going to plug 20% into our y and calculate and solve for x. And in this case, we get a functional sensitivity, LOQ, of 0.358. That makes sense. We don't like to do it mathematically like this. This is totally legitimate. CLSI is fine with it. But this is really hard, we find, once it's in production to actually be able to maintain that because you're going really down to the bleeding edge of that assay. Is it reproducible? Yeah. Is it difficult to run CalVARs all the way down there? You betcha. So unless it's something that's really clinically valid, we typically just go with the functional sensitivity levels as shown above. So let's talk now about LOD, limit of detection. This is a CLSI document that I used to put this together, the evaluation of detection capability for clinical laboratory measurement procedures. So let's talk about what LOD is versus LOQ. The LOD describes the threshold above which analyte values can be distinguished from blank. So at what point, how low can I go before what I'm seeing is really just noise? We're not looking at precision or accuracy, we're not looking at error, we're not looking at CVs, just where is that noise cut? So this example here, let's say that our LOQ and our upper limits, this is our reportable range, as determined by the aqueous linearity, was 0.98 to 1,000. And then our LOD, as described, I'll show you how we find that in a minute. Let's say in this example that it's 0.05. So this area in green is our reportable range. This is where we're going to report patients between 0.98 and 1,000. Anything above 1,000 we're going to call greater than upper limit. Anything less than the LOQ, we're going to say it's not reportable. So you might then ask, why do we care about the LOD? If we're never going to report a patient below 0.98, then why do we care where that LOD is? And that's a really good question, and I've questioned that quite a bit myself. But what I've found over the years is it's very helpful to understand where that noise threshold is for your instrument and for your assay, because we hope that in most cases, this gap between the LOD and the LOQ is significant. But in some cases, our LOQs go pretty darn low, and we get that LOD and the LOQ start getting closer and closer together. And the danger of that is, of course, if you start to have assay problems, or your instrument gets really dirty, or your instrument starts malfunctioning, or just ages, that LOD, the noise threshold can start creeping up a little bit. So understanding where your LOD is in relation to your LOQ will help you with troubleshooting, will help you understand when things are starting to age out. So I find this very easier to show graphically using chromatography. So this is answering. This is at our LOD, limit of detection. You see those purple peaks? This is 3 replicates of where our LOD is sitting. Are those purple peaks peaks? Sure. Are they real peaks? No, they're not, because you really can't differentiate between the purple peaks and the yellow peaks. Those are pretty much the same size, the same. It'd be really easy to accidentally grab one or the other. They're also, if you can tell between these 3, they're really inconsistent as far as reproducibility. This is our LOQ on the bottom here. You see how this is that green peak? Can you differentiate that green peak from those little tiny nubs next to it? Absolutely. So this is graphically, I think it helps to see what LOD looks like versus LOQ. So the LOD and the LOQ are critical when detection of really small amounts are necessary. So there are a few cases where our assay, we will report all the way down to the LOD, and we're very careful about doing that. We only do it when any sort of exposure is absolutely critical. Like we have a few of our toxicology assays in our Atlanta facility where any level of detection is bad. So if your result falls in between the LOQ and the upper limit, we're going to give you a number. If your result falls between the LOQ and the LOD, we're going to say was detected, but we're not going to give you a number, just so that the clinician understands that we saw this chlorinated pesticide, but it was too low for us actually to quantify. So at least they're aware that there was some level of exposure. We don't do this very often, and this has to come from a lab director decision, and it has to be clearly communicated with our clients in medical affairs so that everyone understands that when you're getting way down towards the LOD, you are compromising a little bit of accuracy and precision. So we don't like to do it unless it's really necessary. So how do we calculate LOD? This is how we've been doing it. We run 20 replicates of the blank, and then we calculate the 3 SDs. So it's a mathematical representation. There is a lot of conversation now about other ways to do LOD. CLSI and the FDA have several recommendations, and some of them are up to 60 replicates of the blank, and then using various equations, parametric and non-parametric analysis to look at the data. We're currently talking about what are the best methods for looking at LOD and how do we define it and how do we speak to it. So this is just a heads up that this is something that may or may not change. We're evaluating it. I took several sets of data recently and looked at it multiple different ways to see what would happen. For example, we had the one we were just looking at where our method gave us a LOD of 0.05. I tried the other 2 methods and got LODs of 0.03 and 0.04. So you can see they're really similar. And actually, in the few cases that I tried out, the current GDX method is actually a higher or more conservative estimation than the other 2. So we feel fine about what we're doing right now. It's something we may do as continued improvement. And in any case, whether we set it at 0.03 or 0.05, the LOQ on this assay is 0.98. So we're never getting anywhere near the LOD anyway. It's just nice to understand what the blank looks like. So once you've got all this data, we're gonna do a write-up. And for the linearity, this is the statement that comes straight out of the CLSI document that says, let's use 1-methylhistidine, for example. For 1-methylhistidine by LCMS, the method has been demonstrated to be linear from 0.98 to 1,000 within a 20% CV and a 20% error. That's what that might look like. And then you would show your chart and your graph as supporting data. So once we've launched an assay into production, that linearity is confirmed every 6 months. And by confirming that linearity, then it is confirming the integrity of that curve. And it confirms that, when we were talking at the very beginning about the ability to interpolate points, the patient results in between each of the calibration points. Doing this every 6-month calibration verification or linearity is just ensuring that relationship is still there and that we're still providing accurate results. So we choose 4 to 6 concentrations throughout the stated linear range. We do, again, 2 or 3 replicates at each level, and we look at, again, CVs and error. I want to point out here, too, to the development staff that when operations is looking at their calvaires, they're assessing their results based on the CV in the area that you were setting during validation. So it's a very conscientious choice that we need to make sure we're making in CV and error, that we're setting that where we expect the assay to perform. So we don't want to make it too broad so that we're not catching when things happen, when there are problems in the assay, we're not catching problems, but we also don't want to put them so tight that they're not able to pass their regulatory requirements. So I'm going to show a few examples of what these look like in operations. Our many labs in our Duluth lab use EP Evaluator, so you can see this shows the linearity, it gives you the slope and the intercept, the percent recoveries, and CVs in between the replicates. This is an example from our Asheville chromatography lab. It shows the acceptability criteria, the experimental design. It shows you the CVs, the errors, and linearity, just like in validation. And then here's another one that's used in the Asheville lab. Again, it's giving you the same information. Here's the expected reportable range. Here's the R squared. Here's the CV and the recovery. So there's different ways that we present the data, but it's all giving the same information. So the take-home points today: calibration curves are a measuring stick. If we can matrix match them, that's great. We use linearities to confirm the calibration. Always, 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 always use a second source. If you can hear anything from this presentation, that's what I want to say. Always use a second source. That's going to be your first sign that something's going on. Then we assess our data looking at CVs, errors, and linearities, critically looking at your data for errors, outliers, that sort of thing. Matrix linearities, comparing those to your aqueous linearities, will give you some indication about whether you're likely to hit any matrix challenges as you move through validation. And then understanding the difference between your LOD and your LOQ are helpful in just understanding the performance at the bottom end of your assay. So thank you for listening to my training. If you'd like to get credit in UltiPro, this is listed as development training linearity. Remember to push the little all button on the view. That's what I always forget, and then I can't find anything. So thank you again. We will be having more technical trainings on accuracy, on precision, on stability, on reference ranges. If there's other topics you'd like to hear about, please shoot me an email. I'm Ashley Gibbon in the development group. Thank you.